Good evening everyone. I welcome you all to the problem solving session of the NPTEL course on thermodynamics. So today we will see some problems on the week 6 assignment and then some problems related to the steam problems that can be solved with steam tables. So first, pure water at atmospheric pressure is at 0 degree Celsius. When it is heated, its specific volume increases steadily, decreases steadily, first increases and then decreases, or first decreases and then increases. So there is a peculiar property of water that if you plot the density to the temperature at so say this is 0 degree Celsius and this is 4 and then so this is 50 degree Celsius, the density becomes maximum at 4 degrees Celsius, and what at 0 degrees Celsius, even at 0 degrees Celsius it is lower, density becomes maximum at 4 and then it drops further and drops if you heat it further. So at 4 degrees Celsius the density of the water is at maximum. So this may not be like the difference may not be very significant like this, but there is a small increase in density till 4 degrees Celsius and then only it decreases. So in terms of specific volume, which is inversely proportional to the density, it will first decrease and then increase. For water, the critical pressure is approximately 22 bar, 221 bar, or 2212 Pascal or 221 megapascal. So the answer is 22 bar or 22.1 megapascal. This can be seen from the steam table. With reference to the steam table provided, the specific volume for saturated water vapor in meter cube per kg at 4.8 degrees Celsius is dash. Note correct up to 3 decimal places. So water vapor at 4.8 degrees Celsius we have to find. So this is the steam table, and first we have the pressure table. That means the properties are given for some particular saturated steam pressure, and then next page we have for the temperature table. So our we have the steam at 4.8 degrees Celsius. So that means we have to interpolate between the first two temperatures, so that is 0.01 and 5 degrees Celsius, and it was asked for specific volume. So I would note down for temperature 0.01 and 5 specific volume of the saturated vapor, so that is Vg. So that is this value and this value and this value. So 205.99 and next one is 147.01. So for interpolating, we want to interpolate to 4.8 degrees Celsius. So using straight line equation, we have y minus y1 by y2 minus y1 equal to x minus x1 by x2 minus x1. So considering y as Vg, we have Vg minus y1 is, so this we can take as first and this is second point. So at first state we have 205.99 divided by this is 147.01 minus 205.99. This is equal to so this is the new state, that is 4.8 minus x1 is 0.01 divided by 5 minus 0.01. So Vg can be calculated. We will have 205.99 plus 147.01 minus 205. This is 4.79 divided by 4.9. Can you calculate this? Hello? Hello? சொல்லுங்க. சொல்லுங்க. ஹலோ. இல்லை, நான் இப்போ ஒரு கிளாஸில் இருக்கேன். ஓகே, நான் கொஞ்சம் கழிச்சு. ஹலோ. சொல்லுங்கள். சரி, நான் வேறு ஒரு நம்பர் அனுப்புகிறேன், ஃப்ரெண்ட் நம்பர் அனுப்புகிறேன்.
143.37. 149.37.
So this will be 149.374 meter cube per kg. So in the next problem we have to find the internal energy of a saturated liquid at 4.6 degrees Celsius. So again we will have the same temperatures. Internal energy of the saturated liquid. So we have Uf. So it is 0 and 21. Now using this one, we will have Uf minus 0 divided by 21 minus 0 on one side, and for the temperature we have 4.6 minus 0.01 divided by 5 minus 0.01. So Uf is equal to 4.59 divided by 4.99 into, I think it is 0 here, into 21. Can you calculate this?
So 19.31 meter cube per.
Do you have any questions with the problem so far? the degrees of freedom for a pure substance and its solid, liquid, vapor triple point is 0. So at triple point you specify the specific volume and temperature and pressure, so all parameters are specified, so then you cannot have any other degree of freedom. So for example, at saturated line you can, at saturated line, if you're asked for the degree of freedom for the saturated liquid line, so this is a saturated liquid, then you can specify a pressure which will correspond to some temperature. So you can have pressure varying from say 1 bar to say 200 bar, and correspondingly you will get a temperature. So in this case you have a degree of freedom of 1. And when you are asked to find the degree of freedom of vapor phase, like liquid vapor phase, like a mixture, then a particular point can be specified by mentioning the pressure or the temperature and the dryness fraction. So dryness fraction will be x equal to mass of the vapor divided by mass of fluid plus mass of vapor. So this is dryness fraction. So in a mixture of liquid you have 2 degrees of freedom. But for a triple point you do not have any degree of freedom. The specific volume of steam after expansion in turbine is 13 meter cube per kg. At this pressure, the saturated liquid and saturated vapor specific volumes are 0.002 and 16 meter cube per kilogram respectively. The dryness fraction of the steam is dash up to correct up to 2 decimal places. So we are given that the specific volume is 13 meter cube per kg, and at this condition the saturated liquid will have a volume of 0.002 meter cube per kg, and saturated gas will have a vapor will have a specific volume of 16 meter cube per kg. Now we have to find the dryness fraction. So the final specific volume can be written as the specific volume of the saturated liquid plus dryness fraction into specific volume of the Vg minus Vf. So now you can simplify when compared to this 16, 13, this value is very low, so you can neglect the value f. You can also simplify this to V is x into Vg, x equal to V by Vg, that is 13 by 16. So this is 0.8125. Or if you want to include, if you do not take the assumption of neglecting Vf, you can also check how different you get from the actual value. So this is 13 equal to Vf is 0.002 plus x into Vg is 16 minus 0.002. So x will be 13 minus 0.002 divided by 16 by So this is again 0.81. Pressure equal to 1 megapascal and temperature equal to 100 degrees Celsius. So it's 0.1 megapascal and 59 degrees Celsius, 0.01 megapascal and 99 degrees Celsius, and on the right we have superheated, subcooled or saturated. So we know from this for temperature equal to 100 degrees Celsius, the saturated pressure is or 0.1 megapascal. So that means this case is the first case is a subcooled, is at subcooled state. But it is given 150.
Sir, by just seeing the temperature we are telling, or
did you understand this, or
by just seeing the temperature we are assuming, or by comparing with the temperature or pressure? Just seeing the temperatures we are
I cannot hear you, sorry. Can you talk Rahman?
yes sir. Sir, but by just seeing the temperatures we are choosing the options or considering temperature also.
Okay. First of all, I by mistake I had put my headphone on mute. If you had talked something earlier and I missed it, please let me know.
Okay sir. No
Did
problem sir. Okay.
you had any previous questions?
No sir, it's
Okay.
no,
So
having no doubt sir.
Okay, here in this case we know this one we know at 1 atmosphere the boiling temperature or the saturation temperature is 100 degrees Celsius. Okay, so this is equivalent to 1 bar, like approximately equivalent to, and then it is equal to 0.1 megapascal. Using this information itself we can solve this entire problem. So for the first case we know at if the temperature is 100 degrees Celsius the saturation pressure is 1 bar or 0.1 megapascal. Any pressure more than that means it is at subcooled state. You can understand this, right? Because of the, if you go to the vapor dome, we have P and S. So this is pressure of 1.1 megapascal, and this temperature is 100, and this is P of 1 megapascal. It is going to be, we don't know what it is, but it is going to be more than 100. So that way,
Yes, sir.
yeah. So if it is 1 megapascal and the temperature is here, so it is somewhere here, this point. So this is at subcooled state. Okay, this is fine.
Okay, sir.
Yeah.
Right.
Yeah. Similarly, at second state, 0.1 megapascal. So that is this pressure line, and the temperature is 159. So for temperature 159, it will be somewhere like this, and that is this point. So this is outside the vapor dome and on the right side of the vapor dome, which means it is a superheated state. And similarly for the third one, we know that it is 99 degrees Celsius, so it is somewhere just close to 100 degrees Celsius.
100.
Yeah, and then the saturation pressure will be slightly less than 1.1 megapascal, but they have given it as somewhere like this, 0.01 megapascal. So that means it is also it is at this state 0.1 megapascal, and 99 degrees Celsius will be again going to be on the right side of the vapor dome. So this is also superheated. So if you are have some confusion, you can also check in this thing. So for 0.01 megapascal, this is the one. The saturation temperature is 45 degrees Celsius, but in the problem it was 99 degrees Celsius. So it is outside the vapor dome and it is superheated. And similarly for 0.1 it is 99, but it was given 159. And for 1 it is 179, but it was given something around 100. So that means it is subcooled liquid.
Okay, sir.
In the next problem, water contained in a piston cylinder assembly undergoes two processes in series from an initial state where the pressure is 1 megapascal and the temperature is 400 degrees Celsius. Process 1 to 2, the water is cooled as it is compressed at a constant pressure of 1 megapascal to the saturated vapor state. Process 2 to 3, the water is cooled at constant volume to 150 degrees Celsius. So this to represent this in a TS diagram, we have initially 1 megapascal and 400 degrees Celsius. So in the process at the end of process 2 or the state 2 is going to be at the saturated vapor state after cooling. So that means initially it was at superheated state, or we can also go through the steam tables and check. Like 1 megapascal, the saturation temperature is 180 degrees Celsius, so like 179.7, and that means 400 degrees Celsius steam is superheated state. So we consider a pressure line here representing T equal to 1 megapascal, and this is, as per steam table, it is 179.9 degrees Celsius. But our the point is somewhere here, mention that is on this line, but 400 degrees Celsius. So now when it is cooled from the at constant volume, constant pressure to 1 megapascal, it should have reached this state. So this is 1, this is 2, and from there it is cooled at constant volume to 150 degrees Celsius. So it is cooled to 150 degrees Celsius, but it could be somewhere here inside. We do not have the volume in the TS diagram, so we can go through the steam table and then get this third point. So we need to calculate the specific internal energy of the water at the final state. So U1 okay. So you can calculate U2. U2 will be at 1 megapascal the saturated vapor state internal energy. Yeah, this one, internal energy. And then then we know V3 is equal to V2, right? Because the it is undergoing a constant volume process between 2 and 3, so the volume initial and final should be the same. Now if you know V2, then we can calculate V3 and then find the internal energy. To calculate V2, we want to know the so V2 is at 1 megapascal and saturated vapor phase. So this is 1 megapascal, and you would have seen here. So this is pressure, temperature, volume, energy. Energy means internal energy, enthalpy and entropy. So we are looking at this column, Vg column, for 1 megapascal. So that is 0.1944. So this is 0.1944 meter cube per kg. Now we know the third phase is somewhere inside the vapor dome at 150 degrees Celsius. So then we can look into the table for 150 degrees Celsius in the temperature table, and we get the specific volume like this. So this is VF3 is 0.001099 0.001091, and VG3 is 0.3925. Oh, sorry, I think this is not because this is at yeah, I think we are on right track. So this is the thing. So now we have V3 is equal to VF3 plus dryness fraction at third state into VG3 minus VF3. So now we know VF3 value is very low and it can be ignored. So we will have X3 is equal to V3 by VG3. So that is V3 is same as V2 state because it is a constant volume process. So it is 0.1944 divided by VG3 is 0.3925. This is 0.4953. Now if we calculate internal energy at state 3, this is UF3 plus X3 into UG3 minus UF3. So this can be obtained from the table. UF3 is 631.7 and X3 is 0.4953 into, and UG3 is 2559.1 minus UF3 is 631.7. So this way you can calculate the internal energy of the third state. So this is 1586.10 0.34 kilojoule per kg. Choose the correct statements in reference to steam tables for water. The enthalpy of vaporization increases with increase in pressure. So this is the, if you remember the steam tables, this is the vapor dome. On the left side is the saturated liquid line, on the right side we have saturated vapor line, and these are constant pressure lines. So this is P1 and P2, P3. So as we go upward, pressure increases. Now this is the this is TNS, and the latent heat of vaporization is the area under this curve. So if we want to cross this process at P1, if we want to make the liquid to vapor, so this is the amount of energy that we will be spending, Ts. This is the enthalpy that is given. Q is equal to T into delta S. So as we go towards the top, the latent heat of vaporization will be lesser, and at this critical point the latent heat of vaporization is 0. So the enthalpy of vaporization increases with increase in pressure. So as we increase the pressure, the enthalpy of vaporization actually decreases. So this is not right. The enthalpy of vaporization is highest at critical point. Actually it is 0 at critical point. So this is also wrong. As pressure increases, the saturation temperature increases. So that is right. So as pressure goes up, the saturation temperature also keeps increasing. So this is right. The enthalpy of vaporization decreases with increase in pressure. This is true. Next, commentator for questions 10 and 11. 0.4 meter cube rigid vessel initially contains saturated liquid vapor mixture of water at 100 degrees Celsius. The water is now heated until it reaches critical state. So the mass of the liquid water at the initial state is dash kilogram. So we have a constant volume rigid container of 0.4 meter cube, and initially it was at 100 degrees Celsius, and heat is supplied inside such that the liquid vapor mixture inside the container will go to the critical state. Now at critical state we know what is the specific volume, so that is V2 or V critical, and then using that and the volume we can calculate the total mass. So at critical state, that is here, we have 0.003106 meter cube per kilogram, and so this is same as volume 1 because the container is rigid and the volume is not changing while we heat. Now at this one, at first state 1, we also know the temperature is 100 degrees Celsius. So this, we are using this, we can calculate, we can, from the table we can get Vg1 and Vf1. So Vf1 at 100 degrees Celsius is 0.001044, and similarly Vg1 is 1.672. So now we know V1 is Vf1 plus dryness fraction at state 1 into Vg1 minus Vf1. So this is 0.003106 is equal to Vf1 is 0.001044 plus x1 into 1.672 minus 0.001044. So with this you can calculate x1 as 0.003106 minus 0.001044 divided by 1.672 minus 0.001044. So this is 1.23 into 10 power 134 into 10 power minus 3 in dryness fraction. It doesn't have limit. Now we have to calculate the mass of the liquid water at the initial state. We know total mass can be calculated using the second state. So that is V2 is 0.003106 meter cube per kg, and volume V1 or V2 both are same, that is 0.4 meter cube. So mass can be written as V1 by V2 or V2 by V1. This is 0.4 by 0.003106. That is 128.783 kilogram. So this is the total mass, and we know there is a dryness fraction of some 1.234 into 10 power minus 3. So we know dryness fraction is dryness fraction is mg2 by mf2 plus mg2. So the denominator we know, and the left hand side is also known. Left hand side is 1.234 into 10 power minus 3 is equal to mg2 is what we have to calculate, divided by 128.783. So now mg2 can be written as 128.783 into 1.234 into 10 power minus 3. Now mf2 is m total minus mg2, so that will be 128.783 into 1 minus 1.234 into 10 power minus 3. So this dryness fraction is very less, so we could have also taken the total mass is the mass of water. So this is 128.624 kilogram. So this is the mass of the liquid water at the initial state. Now volume occupied by the vapor and the at the initial state. So V2 or VG2 is VG1 into mass of the. Now VG1 is, we know from this one, so that is 1.672 into mg1 is this value 128.783 into 1.234 into 10 power minus 3. So this is 0.2657 meter cube. The next question, a piston cylinder arrangement. Piston cylinder device with a free floating piston contains liquid vapor mixture. It occupies a volume of 0.15 meter cube at a pressure of 600 kilopascal. The steam is heated at a constant pressure until the temperature reaches 400 degrees Celsius. If the contents inside the piston cylinder device weighs 0.5 kilogram, the heat transfer for this process is dash joules. So we know the volume or the initial volume is 0.15 meter cube and mass is 0.5 kilogram. The pressure at the initial state is 600 kilopascal and temperature at the final state is 400 degrees Celsius, and the pressure is constant throughout the process, so we can take P1 is equal to P2, and we have to calculate the heat transferred for the process. So this is a constant pressure process, so heat transfer can be written as H2 minus H1 into mass into H2 minus H1. Now we know we can calculate V1 using these values, and the pressure is known, so then we can calculate the dryness fraction. So V1 is V1 by V, that is 0.15. This is 0.3 meter cube per kilogram. Now if you take the table, the temperature is given as, the pressure is given as 600 kilopascal. Can you unmute yourself? You can, when you have a question, you can unmute and ask. So until then, can you mute yourself? Thank you. So with 0.6 we have we have these two. You know, V1 is equal to Vf1 plus x1 into Vg1 minus Vf1. So that is 0.3 is equal to 0.00110 plus x1 into, this is 0.3156. Now I can approximate Vf to be 0, then I will have x1 as 0.3 divided by 0.3156. So that gives me a dryness fraction of 0.950. Now I can calculate the internal energy at state 1, that is UF1 plus x1 into UF1 minus UG1 minus UF1. So UF1 is 669.7 plus 0.95 into UG1 is 2566.8 minus 669.7. So U1 can be calculated. Sorry, actually we need to calculate the enthalpy. So internal energy is what we need. So we calculate H1 into HF1 plus X1 into G1 minus H1. So H is 670 and this. So this can be written as HF1 plus X1 into HFG1. So H1 is 670.4 x1 is also plus 0.95 2085.7. That is 2651.815 kilojoule per kg. Now at the state 2, it is heated to a temperature of 400 degrees Celsius while maintaining the same pressure, that is 0.6 megapascal. So then we know the saturation temperature is 158.8 for this pressure. So this 400 degrees Celsius should be a superheated steam. So that can be obtained from the superheated table. So this is 400 and the enthalpy is 3270.8. So this is pressure 0.6 megapascal or 600 kilopascal, and at 400 degrees Celsius we can calculate we can see the enthalpy, that is 3270.8. H2 is 3270.8 kilojoule per kilogram. Now Q is mass. So Q value we have m into H2 minus H1. So m is 0.5 and H2 is 3270.8 minus H1 is 2651.815. So this is 309.49 kilojoule per kilojoule. We have already multiplied with mass. So in the problem it is asked to tell in joules. So then this will be 309,490 joules. Do you have any questions? in the next problem, we have to find the saturation temperature, the changes in specific volume and entropy during evaporation, and the latent heat of vaporization of steam at 1 megapascal. So for 1 megapascal we can go to the steam pressure table. So this is at 1 megapascal, and saturation temperature we know that it is 179.9 degrees Celsius. So Tsat is 179.9 degrees Celsius. Then changes in specific volume and entropy during evaporation. So we can, so delta V is V2 minus V1. This is Vg minus Vf. So Vg and Vf are here. That is 0.1944 minus 0.00. 1127. So this is the change in specific volume during evaporation. This is 0.193272 meter cube per kilogram. And similarly, delta S is entropy at second state minus entropy at first state. That is entropy G minus entropy F. So that can be found in these last columns. So this is, and this we can say the intermediate S subscript Fg means Sg minus Sf. So it can be directly obtained from here. So this 4.4469. So this is 4.4469 kilojoule per kg Kelvin. And latent heat of vaporization is delta H. So this is again HFG. So this is also SFG. And that is HFG at 1 megapascal. 2014.6. So we have found all the values that is asked. Now the second problem, find the enthalpy and entropy of steam when the pressure is 2 megapascal and specific volume is 0.9 meter cube per kg. So we can go to the 2 megapascal column row, and the specific volume is given as 0.09. You can see the Vf and Vg from the table. So that is 0.001177. Sorry, this is Vf meter cube per kg, and Vg is 0.09959. Using this we can calculate the dryness fraction, and then calculate the properties like enthalpy and entropy. So dryness fraction can be approximated as V by Vg. So this is 0.09 divided by 0.09959. So that is 0.904. So this is the dryness fraction. For enthalpy, we can write enthalpy at state F plus dryness fraction into enthalpy Fg. Sorry, HFG. F. So this is at 2 megapascal. Enthalpy F is 908.5 plus 0.904 into enthalpy Fg, that is 1889.8. So this is 2616.88 kilojoule per mole. And similarly entropy is entropy F plus X into entropy Fg. So this is entropy F 2.4468 plus X is 0.904 into Fg is 3.892. So this is 5.96 kilojoule per kilogram Kelvin. Do you have any questions?
Sir, here in the dryness fraction, we are neglecting VF, sir.
Relating
In the
V to Vg.
denominator,
Sorry.
in the denominator, we are neglecting VF for dryness fraction, sir.
Yes, yes. So we have seen earlier in another problem.
Yes, sir. Yes, because in that problem, that is VF is too small, sir.
Yeah, everywhere Vf will be very small. So even now also the Vf is 0.001177, right?
Right, sir.
So every time you can go to the table also, you will find that all the Vf will be small. So this is relating the volume of the fluid. So volume at liquid state is what Vf is, and volume at vapor state or the gas state is Vg. So this will be very much different. So in all the cases you can neglect Vf.
But practical, we have to consider, sir.
Yeah, maybe when you go to the very high pressures like say 20 bar and all, then these are more, both are comparable. But say till this point and all, say till even at 1 megapascal it is very different. So like 0.5% only we have for the Vf, right? So this way we can also try to solve without neglecting that, and you will see what dryness fraction will do. I will just quickly solve. So X will be we have V is equal to Vf plus X into Vg minus Vf. So X will be V minus Vf divided by Vg minus Vf. So here V is 0.09 minus Vf is 0.001177 divided by Vg is 0.09959 minus 0.001177. So now I have got 0.90255. So earlier I had 0.904, only in the third decimal place some 2 has gone. So the percentage error you will get is very good, it will be less than 0.1%.
Okay, sir.
So in the next problem, steam initially at 0.3 megapascal 250 degrees Celsius is cooled at constant volume. At what temperature will the steam become saturated vapor? What is the quality at 80 degrees Celsius? What is the heat transfer per kg of steam in cooling from 250 degrees Celsius to 80 degrees Celsius? So initially the steam is kept at a constant volume chamber, and initially it is at 0.3 megapascal and 250 degrees Celsius. So now heat is transferred out, so that means it is cooled, and then it has gone to a final state of 80 degrees Celsius, and on the way we can find what will be the steam temperature when it becomes saturated vapor.
Sir, what is that A1, sir? A1 at what temperature?
At what temperature will the steam become saturated vapor?
Okay, sir.
Okay. So now we can calculate, we can find what is the specific volume at this state. It's a given for initial condition. It seemed to be a superheated state. That is why they say after cooling it comes to saturated vapor phase. So V1, 0.3 megapascal and 250 degrees Celsius. 0.3 megapascal, the saturation temperature is 133, but in the given initial state is 250 degrees Celsius, so that means it is at superheated state. So going to the superheated steam table, we have 0.3 megapascal. So it is here, so 0.3 megapascal and 250 degrees Celsius. So this row we are talking about, and we need to know the volume, right? Or yeah, we need to know the volume. So volume is 0.796 meter cube per kg. So this is 0.796 meter cube per kg. We will also need to find the heat transfer, so I will note down the internal energy. So here the thing is in a process is happening in a constant volume chamber, so I do not worry about the enthalpy. I will be worried only about the internal energy. So internal energy is 2728.9 kilojoule per kg. Now at what temperature will the steam become saturated vapor? So now we can find at some temperature T2, the V2 is same as Vg2. So we can calculate the temperature which corresponds to this. So that means we should go to the saturated steam table, and at the temperature chart we need to find where this 0.796 occurs. So here 0.796, so that is between these two. So that means when the at 120 degrees Celsius the saturated steam's specific volume will be 0.89, and at 130 it will be 0.668. So our specific volume is 0.796, which lies somewhere between these. So so we can interpolate the values and get the saturated temperature. So temperature is we can have specific volume and temperature, and that is what we need to find. Specific volumes are 0.8912 at 120 degrees Celsius, and at 130 we have 0.6680, and now at 0.796 we need to find the temperature. So using the linear equation, we will have T minus 120 by 130 minus 120 is equal to 0.796 minus 0.8912 divided by 0.668 minus 0.8912. So T is equal to 120 plus 10 into the difference, so 0.796 minus 0.8912 divided by 0.668. So this is 124.26 degrees Celsius. Now further it is cooled down to 80 degrees Celsius, and we need to find the quality of the steam and the heat transfer. So A problem is solved. Now at 80 degrees Celsius we can find the this one quality. So now we know the since the volume is same, just to be V1 equal to V2 equal to V3, we can find using this. At 80 degrees Celsius we know we have found from the steam table that Vf is 0.001029 and Vg is 3.405. So V3G equal to 3.405 meter cube per kg, and that is same as points or our V3 is 0.796, also the same thing. Now X3 is V3 by V3G, that is 0.796 divided by 3.405. This is 0.234. So this is the dryness fraction at state 3. Now we can calculate the internal energy, or we can find the internal energy. Now UG3 UF3 UG3 can be calculated, and U is equal to UF3 plus X3 into UG3 minus UF3. UF3 is, so at 80 degrees Celsius we have these values: 335 and 2481.6. is what we have to find. 335 plus dryness fraction we have calculated as 0.234, and UG3 is 2481.6 minus 335. So this is 837.3 kilojoule per kilogram. This is at state 3. We already have state 1. Now heat transfer can be m into u1 minus u3. So we have calculated m. Okay, m is not known, so we can have it in terms of per kg. So that is 2728.9 minus 837.3. That is 1891.6 kilojoules of heat is transferred for every kilogram of steam. Do you have any questions?
No, sir. But with the we can check the quality of the steam by using our dryness fraction, no, sir.
Dryness fraction is the quality of steam. So after this I have found the heat transfer. So this is heat transfer.
Yes, sir. We can assuming mass as 1 kg, sir.
Yeah.
Instead of neglecting.
Yes. So or we can write the answer in terms of per kg. So,
Per kg. Okay, sir. Understood, sir.
Thank you. Next problem. A steam boiler initially contains 5 meter cube of steam and 5 meter cube of water at 1 megapascal. So there is a boiler, 5 meter cube of water and 5 meter cube of steam at some pressure of say 1 megapascal, and now steam is taken out. Is taken out at constant pressure until 4 meter cube of water is left. What is the heat transfer during the process? So some heat is also transferred to maintain the pressure, and some mass of steam is taken out such that the final become, so this is 5 meter cube and 5 meter cube. At the end of this we have 4 meter cube, and the remaining has to be 6 meter cube, right? Four meter cube of water and 6 meter cube of steam is left finally. So with this we can calculate the ms, and then also we can balance the energy and get the heat transfer. To balance the energy, we have U initial and some heat is supplied on one side, like in the initial state. On the final we have the final internal energy of the steam or steam water or the boiler contents, plus there is some mass of steam is taken out which carries some enthalpy with it. Okay, so initially we have some internal energy, so this is initial we had some internal energy and some heat is transferred, and then that became a final thing of some system, similar system with some different internal energy. And we have also taken out some enthalpy of the steam with some ms. So mshs is the energy that is taken out. So this way we have balanced the energy, and we are getting the we can calculate the Q. So initially for UI we can calculate based on 5 meter cube steam and 5 meter cube of water. We can calculate M1 as or we will take the VG, VF and VG. It is going to be the same initial and final because the state of 1 megapascal is not changed. So going to the steam table, for the pressure, in the pressure table we have this two VF and VG, that is 0.001127 0.001127 meter cube per kg, and for VG we have 0.1944 meter cube per kilogram. Now we can calculate the total mass M. It is going to be the same, no, M1, because it will be different in the second state, or M initial. So that is volume of the fluid by specific volume of the fluid plus volume of the gas by specific volume of the gas. So all these are first state. Now total volume of the fluid or the liquid at first state is 5 meter cube divided by the specific volume is 0.001127 plus the volume of the gas state or the vapor state is 5 and the specific volume is 0.1944. With this you can calculate the total mass.
Double 462.27.
Can you also get this individual mass, like mass of the fluid alone and mass of the liquid alone?
What, sir?
The individual mass, so mass of the fluid alone and mass of the vapor alone.
So 4436.55
36.55 plus
plus 25.7, sir.
25. So initial mass is calculated. Now we can calculate the internal energy as well. So U initial is equal to mass of the gas at first state initial, and then internal energy or UG plus M fluid in the first state, mass of the fluid in first state into internal energy of the fluid at first state. So this is mass is 25.77 mg, 25.77 into UG can be taken from the steam table, that is 761.4. So this is 761.4 plus mass of the liquid is 4436.55 into the UF is from the steam table, it is 2582.7. Can you get the internal energy at the initial condition?
Sir, it's coming like 11, 47, 78, 98.96,
1147,
48, 98, 78, 98.
so 1147, 48, 98.
78, sir. 48 into 7, sir. 78.
Oh, 78. This is right.
Fourth digit, sir. From the right side, it's 7.
Oh,
Fourth
okay.
digit.
Okay.
Uh,
Now,
after 8, it's 98, sir.
okay, 98.
0.96. Sir, UI of what, sir? Internal energy of what, sir?
Internal energy at first state. I is initial state.
Yes, sir. Initial state means our water is decreasing for 1 meter cube.
Yeah.
So
So
that's internal energy.
no,
So
no,
that's internal energy.
no, no. Internal energy of the entire boiler with both the steam and liquid,
Oh.
steam and water. Now, similarly, UF can be found. So that is, or we need to know the mass at the second state. That is V, same as this, Vf2 by Vf plus Vg2 by Vg. So this is Vf2 is fluid, we had 4 meter cube, divided by Vf is 0.001127, right, and plus 6 by 0.11944. So can you get these individually?
Sir, VF2 by VF is 3549.24.
3549.24. Second term
30.89.
30.89, and this total is
3580.10.
10. So this is the key. So now we can calculate the U final, that is again with the same formula, mg2 ug plus mf2 uf, and mg2 is the second term, the previous thing, so this is 30.89 into ug2 is 761.4. I think we made some mistake. The UG is the one with the higher value, right? So this is 2582. This is 2582.7 plus mass of the fluid is 4436.55. 4436.55 into this is UF is 761.4. So I just interchange these two values, sorry. Can you calculate UI again? Sorry.
Sir, UI is 3445,
3445.
432, 432.65.
So
432.
I am getting 34454. Is this right?
I am getting in last I am getting 432, sir. We are getting 545.
545. Okay.
Around 100 is.
Yeah, yeah. I think that is okay. Okay, fine. So this much of kilojoules. And similarly here we will have 2582.7 plus MF2 is 3549.24 into UF2 is 761. Can you calculate this UF?
Sir, it's 2782,
2782.
170.93.
190 kilojoules. So now we have calculated U initial and U final. Now we want to calculate the enthalpy lost in the steam. So excess can be obtained from the table. So that is 2777.1. This is Hg. So that is 2777.1 kilojoule per kg. And we know ms is also ms is m1 minus m2 plus 4462.27 minus 3580. So this is ms. Can you calculate ms?
Sir, 882.6.
882.6 kilogram. Now we can calculate MSHS. So that is the enthalpy lost. That is 882.6 into 2777.1.
So 2445.68.
2445.68
.46.
Now we know UI plus Q is equal to UF plus MSHS. So Q is equal to UF is 2782.170.93 plus 244568 minus U initial, that is 344454. Can I calculate Q?
So 4178.06 negative.
No, we are getting negative.
Yes, sir.
able to find any mistake in that?
No, sir. No, sir. All seems correct.
I have got a different value here. So this I am getting as 2451068 kilojoules. Can you recheck once this 882.6 into 27777.1? Then it will be 245.106.
Yes, sir. It's 24 510, sir.
51068, no? So then maybe this will make sense. Can you calculate the value of Q?
So 1788
6, yeah.
693.98.
So this much of joules. So writing in terms of megajoules, we will have 1788.7 okay. Problem is clear.
Yes, sir. In at the starting, sir, can you just sir, why we are going like this, sir? UI plus Q equal to UF plus MS into HS, sir.
So
At Q equal to M into like in previous problem we are using formula for Q equal to M into UF minus US बोल के.
where was it?
No, sir. Just it previous one.
Yeah, some previous problems you would have used. So we need to see if there is if the problem contains only some constant volume chamber, and then you add some heat and take work and all, then you can go to this initial formula, that first law formula.
Yeah, yes, sir.
Yeah,
Thermodynamics first law.
thermodynamics first law. So here, if it is constant volume, then W will not be there, right? If there is only some constant rigid wall always. So then I can write Q is equal to delta change in internal energy. Okay, I will note down, write somewhere else. So when we have constant volume chamber, I can write delta U plus W, and there won't be any heat transfer, so I will write, because delta V is 0 and there is no work transfer. So everything happens in a constant volume, and I only add heat or take away heat. So for this I am worried only about the internal energy. And in this current condition, we have a constant volume case, but there is some heat or some heat is supplied inside Q, and there is a mass of steam that is taken outside. So the mass of the system itself keeps changing. So then you have to go for the steady flow equation. So where we have internal energy of the initial plus heat transfer is equal to internal energy of the final state. So internal energy by meaning internal energy, this internal energy of the contents inside the constant volume, and then there can be some work transfer out, that is done by the system, and there can be some mass of fluid that is coming out with an enthalpy of out, and there can be some mass coming in with an enthalpy inlet. So now in this case we didn't have any work transfer, and there is no energy that is given inside, or there is no mass of gases or something entering inside, so this is also 0. So finally we end up with mass of initial plus heat transfer equal to UF plus M0.
Yeah. Okay, sir. Understood, sir. 1 second, sir.
Yeah.
Yes, sir. Continue, sir.
Yeah, thank you. So you can unmute, and you can mute now and unmute when you have questions. 280 mm diameter cylinder fitted with a frictionless leak-proof piston contains 0.02 kg of steam at a pressure of 0.6 megapascal and a temperature of 200 degrees Celsius. The piston moves slowly outwards through a distance of 305 mm. The steam undergoes a fully resisted expansion, during which the steam pressure P and the steam volume V are related by PV power n is equal to constant, where n is a constant. The final pressure of the steam is 0.12 megapascal. Determine the value of n, the work done by the steam, and the magnitude and sign of heat transfer. So the steam undergoes a polytropic process given by PV power n is equal to constant, and first step is to find the value of n. So to find the value of n, we can have PV power n is equal to constant or then that means P1 V1 power n is equal to P2 V2 power n. Now if you take log on both sides, natural ln of P1 plus ln of V1 power n is equal to ln of P2 plus ln of P2 power n. So finally you can have ln of P on one side, and then you can have n into ln of V1 minus ln V2 is equal to ln of P2 minus ln P1. So this is N is equal to ln of P2 by P1 divided by ln of V1 by V2. So now we know the initial pressure and the final pressure. So that is P1 is 0.6 megapascal, P2 is 0.12 megapascal. The volume at the second state is not given directly, but delta change in volume is given by the diameter change in the diameter and the distance that the piston moves. So that is pi by 4 d square into x or L, the length by which it has moved. And similarly, mass is given as 0.02 kilogram of steam. So the initial of 0.6 megapascal and 200 degrees Celsius is given. So this should be such superheated steam, which can be seen from the table also. So the pressure is 0.6 megapascal, 0.6, and the temperature is 200 degrees Celsius. So the saturation temperature is 158.8 degrees Celsius as from the steam table. Since our state is having 200 degrees Celsius, so it is a superheated steam. And we can go to the superheated steam table, 0.6 and 200, and then using the specific volume and the volume or the mass given, we can calculate the initial volume. So this initial specific volume is 0.3521. So V1G is 0.3521, or this is V1 meter cube per kilogram, and mass is given as 0.02. So V1 is m into V1, so that is 0.02 into 0.3521. So can you calculate V1?
Sir, V1 is 7.42 042 into 10 power minus 3 meter cube.
Okay. Now delta V can be found. Delta V is pi by 4 d square into L. So this is pi by 4 into d is 280 mm, so that is 0.28 the whole square, into the length is given as 305 mm, so that is 0.305 in terms of meters. So can you calculate delta V?
So it's coming as 0.018.
0.018 meter cube. So delta V is V2 minus V1. So V2 is delta V plus V1, that is 0.018 plus the V1 value, that is 7.042 into 10 power minus 3. Can you calculate V2?
Sir, it's 0.025.
So now we know ln is equal to sorry, n is equal to ln of p2 by p1 divided by ln of v1 by v2. So that is ln of p2 is 0.12 and p1 is 0.6, 0.12 by 0.6 divided by ln of v1 by v2. v1 is 7.042 into 10 power minus 3 divided by v2 is 0.025. Can you calculate the value of n?
So it's coming as 1.27.
Yeah, 1.27. Now we need to calculate the work done by the steam and the magnitude and sign of the heat transfer. So any idea how we can do this using the concept that we have learned earlier?
We can take work done from the polytropic process.
And what is it? Okay, it is P1 V1 minus P2 V2 by n minus 1. So if you don't remember every time, you can also quickly derive and see. So this is P into integral P delta dV. Now write pressure in terms of volume. So we have PV power minus equal to constant. So that means pressure is equal to constant by V power n. So we will have work done is equal to some constant into dV by V power n. So constant term can be taken outside, and we will have dV integral dV by V power n. So this constant into this is V power n minus 1 divided by n minus 1, and this constant is PV power n. This will be within the limit V2 to V1. So this is V2 n minus 1 minus V1 n minus 1 divided by n minus 1. So this constant can be this C will be P1 V1 power n or P2 V2 power n. So this can be written as P1 P2 V2 power n into V2 power n minus 1, or is it n plus 1? Sorry, when we integrate it is n plus 1.
Yes, sir. Denominator also.
No, I think it is this is integral b power minus n into v. So then we will have v power 1 minus n by 1 minus n. This is v2 into v2 1 minus n minus v1 So now C is P1 V1 power n or P2 V2 power n V2 power n minus n minus P1 V1 power n V2 power n minus n by n. So then we get P1 V1 minus P1 V2 by n minus 1. So this is the formula we have. So work done P1 V1 minus P2 V2 by n minus 1. So P1 is known, that is 0.6 megapascal. 0.6 into 10 power 6 into V1 is 7.042 into 10 power 7.042 into 10 power minus 3 minus P1 is 0.12 megapascal into 10 power 6 and V2 is 0.025 divided by n minus 1 is 0.27. So can you calculate the value of work done?
Sir, it's 45, 37.77.
0.77 joules per kg. It is not per kg because we have put the value. So now we need to find the magnitude and sign of heat transfer. Now we know Q is equal to delta U plus W. We can calculate the internal energy at the state 1 and 2 and then we can calculate Q. Internal energy at state 1 or the initial state is from the superheated steam, right? It is from the superheated steam, that is 0.6 megapascal and 200 degrees Celsius, that is 2639.3. So U1 is 2639.3 and into mass we want, so okay, it's okay. So we will have U1, this is kilojoule per kilogram, and similarly you can calculate U2, and U2 we do not have any direct clue, so we have to take the volume and then find. So we know at the state 2 we know only the volume and pressure for now, and using this we have to find the internal energy. Volume 2 is the pressure 2 is 0.12 megapascal and volume 2 is 0.025 meter cube. Now the specific volume can be calculated as V2 by M. V2 is known as 0.025 and M is given, it is 0.02. So with this we can calculate the specific volume.
So it's 1.25
meter cube
per kg.
per kg. So if you go to the steam table, and this is pressure is 0.12 megapascal, and you can first check in the saturated state. So 0.12 megapascal, the saturated steam itself has a specific volume of 1.428, so but our is 1.25, so that means we can calculate some, it should be within the vapor dome, and that can be calculated. So x2 is V2 by Vg2, that is 1.25 divided by 1.428. And calculate it, dryness fraction
Sir, getting at 0.875.
0.875. Now u2 is equal to uf2 plus x2 into u2 minus uf2. So uf2 is 439.2 plus 0.875 into ug2 is 2511.7 2511.7 minus 439.2. and calculate u2.
Sir, 2252.63.
0.63. Now delta u is m into u2 minus u1. That is m is 0.02 into 2252.63 minus u initial is 26393. And calculate delta u.
Sir, it's minus 7.7.
7.7. Minus 7.7 is in
3.
joules, right?
Yeah, 3
Okay, joules. No, I think it will be in kilojoules. It will be in kilojoules
Yes.
because this 225. So now Q is equal to delta U plus W. Delta U is minus, we can write in joules because W we have calculated in joules. So 7730 plus work transfer is 4535.77. Calculate the value of Q.
Sir, it's maths 3194.23.
3194.
3194.
Okay, 0.23 joules. So since it is negative, what do you say? The heat is transferred from the system to the surrounding or from the surrounding to the system?
Sir, it's heat transfer from the surrounding to the system, sir.
No, from system to surrounding.
System to
Because
the surrounding, sir.
yeah, we always take heat transferred into the system is positive, and heat transferred from the work transfer from the system to the surrounding is positive. So I think it's time now. If you have any doubt, I can answer now or you can see in the next class.
Sir, in this problem, sir, in next slide, sir.
Yeah.
Sir, here, sir, at fourth column, what we are doing, sir?
Last column, work done. I have tried to derive the work done. So work done, we know it is integral PdV, right? Here it is.
Yes, sir,
Work done
integral
is
PdV,
integral
right,
PdV.
sir.
Yeah. So here P, I can write P in terms of volume because I know PV power n equal to constant. So I have written
Yes,
P as constant by V power n. Okay.
right, sir.
Yeah. So now I can write this integral instead of integral PdV, I can write integral constant into dV power dV by V power n.
Right, sir. From C equal to P1 V1 power n, sir, sir, from here, sir.
Yeah. So here this constant I know it is PV power n. So this can be given for state 1 and state 2. So C can be P1 V1 power n or P2 V2 power n. So now I have to multiply this constant with V2 and V1. So it is if I put P2 V2 in the first and P1 V1 for the second term, I can cancel out the V and then I can get P1 V1 like this.
Sir, not understood, sir. WD work done, not understood, sir. P2 V2 power n.
Okay. So I will write in few more steps. So now I have work done is equal to constant into V2 power 1 minus n minus V1 power 1 minus n divided by 1 minus n. So now I know constant is P1 V1 power n equal to P2 P2 power n. So now work done is I can write this as constant into V2 power 1 minus n minus constant into V1 power 1 minus n. Right.
Right, sir.
Now for the first constant I write this term P2 V2 power n V2 power 1 minus n. So this is first term, and for the second term I am writing this one P1 V1 because all are same. This is clear?
Yes, sir. Understood, sir. Yes, sir.
Thank you. Do you have any other questions?
Sir, just to go to the previous slide, sir. So after this, sir. Sir, our state 2 is when the piston is coming outward, now the backward,
yes,
now
sir. Yeah, piston has moved out, so it has expanded.
So our second initial state is after the piston coming back, sir.
Second state is after the piston has expanded. So in the first state piston was something like this, and this is first state, and second state it has expanded from the initial position. So this is 0.30.
Okay, sir. Understood, sir.
And may I know about your background? You are doing bachelor's or doing master's?
I am doing. I am undergraduate, sir. I am in graduate. I am a graduate student in 3-2, sir.
Sorry,
in the third year, sir.
Okay, third year. Okay. Where are you
third
from?
Year.
Which university you are from?
Sir, I am from this Usmania University, sir, from Hyderabad.
Hyderabad. Okay. And you are taking this course to audit in your so that you can credit in your university, or just out of interest you are taking?
Sir, for the both, sir. I studied thermodynamics earlier.
Okay.
So for the research purpose and also interest purpose, sir.
Okay. Fine. Nice. Any more questions, or we will close for the session?
Sir, not a big question, sir. Just a little. Sir, for the pressure, we are conducting. For normally we can say this is a 1 atmospheric, 2 atmospheric, or like that in other units. So if I just consider that our atmospheric is infinite, sir.
Hmm.
So for the and air in the atmosphere is also infinite in
Hmm.
the infinite space.
Hmm.
So by just conducting an experiment for the taking mercury in a test tube and at the sea level we are telling that this is 760 mm of Hg. By just seeing this, uh, our space is infinite, air is infinite,
Hmm.
and why pressure is not infinite, sir?
Well, pressure is not infinite. So the pressure you have earth here, okay, and there are air molecules around the earth, right? And after in the outer space, say after some 1,000 kilometers or 10,000 kilometers, there is no air, right?
Yes, sir.
No air at all. So then you can say there is some column of air only, some finite column of air that is pushing the air below it downward.
Yes, sir.
Yeah. So maybe say this is some 100 kilometers of air. 100 is too much, so we can say 5 kilometers of air column. So only that much equivalent of air is present. So then we can calculate because of this air molecule here, it is having a gravity, experiencing a gravity that is downward towards the earth, and that will push the molecule downward. And so similarly, this will push the other molecule downward. This will push other downward. So finally, we got some pressure with this surface level.
Yes, sir.
Yeah. And this gravity at this location outward will not be 9.8. It's not
Yes, sir.
9.81. It will be lesser.
9.8.
Only at this level, surface level, it is 9.81. Okay. Here it is less than 9.81. So it can be 1 meter per second square. It can be. And similarly, the pressure caused by this molecule, air molecule, will not be same as what it is causing at the ground level. Fine,
The
no?
pressure exerted?
Pressure at this after 5 kilometers, if there is a molecule, the pressure will not be same as the ground level pressure.
Yes, sir. Ground level. Yes, sir.
As we go up, the pressure will also vary, and that is because the gravity is also changing, and the air column is also less. Effective air column is also less.
Yes, sir. Okay, sir.
So that is why we do not have infinite, because after some point there is no air at all. So effectively we have only say some finite amount of air column we have.
Okay, sir.
Okay. Any other questions? This is you are convinced with my answer, or
Yes, sir. Understood, but need some more clarity on that, sir. Need some more clarity.
like which part you cannot understand? You can understand that there is no air after some distance, right?
Yes, sir. I understood this also, and about the gravity is not equal to 9.81 is also equal. Understood.
Yeah.
And a molecule of our column is applying pressure
Same.
on the other molecule.
Yeah. So maybe
Yeah.
only for 5 kilometers or 10 kilometers only we have air, right? So now pressure, as we studied earlier, like it is rho gh.
Rho g is right, sir.
Rho of air is 1.18 something. Gravity to effective gravity we can call it is something like 9.81, or I can call this as F effective, because as we go upward it is not 9.81, and only
Right,
here
sir.
it is 9.81, and after we go upward it is decreasing. So F effective is something like 5 kilometer or something. Then 5 kilometers, 5,000 meters. So then I can calculate some finite pressure. This F effective is not infinite.
Right, sir. Not infinite, right?
So there is some finite air column, and then we can have a finite pressure.
Okay, sir.
Okay.
Sir, sorry, our in thermodynamics, what we learn is whole work done is converted to heat, sir. But our whole heat is not converted to work done.
Yes, yes.
Yes, so on the surface we can give an example of see like in IC engine, whole heat is not converted to work done, and by rubbing hands, our putting work in this is converted to heat. So on the what is the question is how thermodynamic encounter this statement, sir? Like how work done is converted to heat, but heat is not converted to work done. Except our with our Carnot engine, we are giving example like not efficiency is not greater than Carnot engine. So what thermodynamic encounter on this statement, sir?
So I think you haven't come across a second law of thermodynamics, right, so far? Or is it already crossed in the syllabus? No, right?
Yes, sir. It's crossed, sir.
Okay.
It's taught earlier, sir.
Okay. So this second law states that for what there were two statements, right? Do you remember?
Yes, sir. One is Kelvin statement.
Yeah.
Another is Clash's statement.
So Clash's statement says there should be two heat body to convert. So there is a heat engine, and there should be always two heat bodies in which the heat engine should be in contact to produce some useful work, right?
Right, sir.
So when there are two bodies, then there should be some Q transferred inside to that can be converted to work. But there is another reservoir, low temperature reservoir, that will be that to which the heat is rejected.
Right, sir.
Yeah, because of this, we can W is always QH minus QL. It cannot be
Right, sir.
W cannot be directly QH. Assuming if we do not have any, if we can have a heat engine with only one this one, and this is not needed, then we can extract heat from our surroundings. So if we have an ambient of say 30 degrees Celsius, we can extract heat and produce work, and then so that the ambient will become 25 degrees Celsius, right? That is not possible.
Okay, sir.
I think you are not convinced yet, right? This you are not you cannot understand why this is not possible, right?
Right, sir.
Yeah, but that is a law. Why it is not possible, I will also try to find, but I think this is the law itself. The law states that based on his experience from Clash's experience or some thing, he has found that it can not be done with only one source. If there are further explanation, I will also try to find in the book, and I will let you know in the next class. You can
Yes,
also
sir,
go through some book.
I remember this law also. But at the starting of this law, what our faculty taught it, the heat cannot be flow from lower to the higher external agency. It's always from higher to the lower.
Yes, yes. Yeah, that is for I think Kelvin statement. So there are two statements in thermodynamics. As you said, Kelvin is about the which says low to high is not possible, and Clash's state there should be two bodies, two thermal bodies to be in contact. Two heat reservoirs is needed. So both statements are comes under the second law of thermodynamics.
Yeah, okay, sir. Understood, sir.
And you can go through some books, Senchel. So he is the author. Okay. And the book name is something like Applied Thermodynamics or Engineering Thermodynamics. I will also go through, if I find some more detailed explanation for this, I will give in the next class. Okay.
Yeah, yes, sir. Yeah, initially I go through that our what one author is there, sir. I can't remember his name. kitchen कुछ है सर नाम तो है इसका but after that I after reading this I not that definitions are too high for me. So I gone for some that RK Rajput, RK Rajput. And after reading RK Rajput, our faculty provide me another another author textbook, like his name is Pakirappa, Thermodynamics by Pakirappa.
Okay.
Yeah, his definition is too close to the his approach is too close what I am reading and approaching about that loss, that too approaching to us. So recently I reading those books.
You can try to get this Angel book and the explanation will be better.
Okay, sir.
Anything else?
No, not really, sir, but that person who is teaching thermodynamics, sir, in the NPTEL,
NPTEL.
sir. So presently watching videos from the NPTEL is that what his name Pranap K Kumar बोल के कुछ नाम था सर उनका.
I think thermodynamics, this course is taught by Professor T.N. Shyam.
Yes, sir. Yeah, TNC, right? TNC Anand, sir, right?
Yeah.
Before this, I used to watch that Pranab Kumar Mandal, sir. Pranab Kumar Mandal, author. Yes, sir. He is also explaining. His explanation is also what I am thinking and getting from this. His explanation is also good, sir. And sir, you are also teaching thermodynamics.
Yeah, I am teaching for this course. I am a PhD student in institute in mechanical engineering. So, as a part of my TA duty, they have assigned me this class.
Okay. In which field, sir?
Mechanical engineering. So,
no, in which topic?
In hybrid powertrain.
Hybrid boundary.
Hybrid powertrain.
Hybrid power plant.
Powertrain, yeah. So for vehicles, for car or two-wheelers, I'm particularly working on two-wheelers. So we will have IC engine plus an electric machine.
Yes, sir. This is hybrid.
Yeah.
But this invention is also
no, you cannot call
new
this
technology, na, sir. This invention is also come to the new technology.
Yeah, but this you cannot call this as invention because these are like more than 20 years old. Yeah, and I'm working on something so that I can improve the existing system, like improving the fuel economy further and reducing the cost, reducing the complexity of the system, something like that.
So generally hybrid power plant. Okay, so you are from automobile or aerospace, sir?
No, I'm from, my background is mechanical.
Achha, background is mechanical only. Sir, is HVAC is good for doing masters or PhD, sir?
That is based on your interest, I would say. If you are interested in HVAC, HVAC, then you should go. It's not like you should not look for the market and what the market needs you go there. I don't prefer that way. You should look for which one you are interested, so that only then you will perform well in that field. Any field you go, if you work with your passion and you put your hard effort, you will always win.
Yes, sir. But what person I met is only my faculty also, which is he is also is HUSC. So other than person who is doing thermodynamic is not HVAC is other than like you are in a hybrid power plant or something else. So that's why generally I ask that is it good or
Yeah, yeah.
is
Every field is good. If you work good, everything will be productive for you.
you are from Bangalore, sir?
No, I am from Chennai.
Chennai. Okay, sir.
Okay. Yeah.
Thank you for
Yeah.
discussion and explaining doubts, sir.
Yeah, sure, sure. See you. Thank you.
Okay, sir.